principal component analysis and spectral clustering. And the reason that I put these two problems like in one talk is that I categorize both of them under the more general umbrella term of representational bias. That's why I wanted to discuss different fairness notions that you can define for different problems in this context. And I would love this to be an interactive talk, so at any point if you have any questions, feel free to interrupt me. Okay. At the beginning, I give you a brief introduction to representational bias. And then I'm sure most of you are familiar with PCA, but I will give a quick overview of PCA problem and what we already know about it. Then I will motivate why it is important to study fairness in the context of PCA and more generally dimensionality reduction techniques. And finally, I will define Fair PCA and propose an efficient algorithm that could be used to generate a fair low-dimensional representation of the data. In the second part of the talk, I will talk about another notion of fairness in clustering, which has been established in the last few years. And I will study how we can incorporate this notion of fairness into the spectral clustering framework. Let's give a bit of history on how fairness started in machine learning. Of course, fairness and equality has been studied in economics and game theory for a long time, but the concerns of bias in machine learning algorithms started by these researchers looking into risk assessment algorithms that were used in Compass, and they observed that these algorithms, they have much higher false positive rates for African Americans compared to white people. Also, they looked into facial recognition systems, and they observed that these systems, they have much higher error identifying darker skin tone female faces compared to lighter skin tone male faces. So these and many other examples started a movement of machine learning researchers looking closer into machine learning algorithms and defining different notions of bias and fairness, and thinking about how to mitigate the bias of these algorithms. So they looked into loan assignment, admissions to graduate school, and recidivism prediction in courts, and many other tasks. What I want to mention here is that most of these tasks in nature are classification tasks. There's a clear outcome that you want to assign to an applicant or a population, and then the definitions of fairness respectively measure how fairly you're assigning this outcome. In this talk, I want to focus on a more subtle source of bias in machine learning, which is categorized as representational bias. And these are the settings where you don't have a clear outcome or product that you want to assign to a person, so you don't disadvantage or affect that person immediately. But what I would like to show is that actually representational bias in machine learning could have disadvantages for minorities in long term when these machine learning pipelines are used over and over again. Here are a few examples. So I searched the word CEO on Google. These are images that Google Image showed me. So most of them are males. So this is not a scenario that I'm assigning loan or graduate admission. So it's not something that affecting the female population like directly. But over the long term, it can have a negative sociological effect on female population and the perception of people from a female CEO. The other examples are there has been studies that showed that when there are advertisements for products or, for example, credit card, some demographics has been targeted and showed credit cards with much less advantage than other demographics. And of course, this is a good strategy probably for the credit card company because they want to maximize the revenue, they want to maximize the probability that the person actually will get that credit card. But from the fairness perspective, one can argue that all demographics could at least be exposed to different offers of credit card. The first problem that I want to discuss in representational bias is bias of principal component analysis. So at the beginning, let me give a brief overview of what is PCA. PCA is probably the most widely used dimensionality reduction technique in practice. And you have a data in high dimensions, and either because you want to reduce the computational burden, or simply just because you want to project your data into 2 or 3 dimensions to look at this visualization and do some pattern analysis, you want to reduce the dimension of the data with keeping as much information in the data as possible. There are 2 formulations for PCA. The first one is in terms of variance. So you're given a high-dimensional data, let's say M. For simplicity, I'm showing it in 2D now. And now you want to find a line on the plane such that when you project this data into this line, you have the maximum variance. For simplicity, let's assume that M is centered, and these data points are represented as rows of the matrix M. Then finding this direction in 1D is equivalent to solving this program. So you want to find a vector x with norm 1 such that you maximize the Euclidean norm of mx. Okay? You can simply solve this program and the solution by writing Lagrange multipliers, and the solution is given by choosing vector x that corresponds to the eigenvector corresponding to the largest eigenvalue of the covariance matrix of your data. So this was going from 2D to 1D. Now you can ask that, what if my data is n dimensions and now I want to go to d dimensions? What is nice about PCA is that it says that you can continue this process 1 vector at a time. So find the first vector. Now look at all the vectors that are orthogonal to the first vector that you found, and now maximize the variance toward that direction. Okay? And this way, keep going till you find your d vectors. And now your the rank D subspace, which maximizes the variance, is simply given by projecting your data into this subspace spanned by the top D eigenvectors of the covariance matrix. Okay, so this was one formulation. The second formulation is in terms of reconstruction error. Reconstruction error of a matrix M, which is your data, when you approximate this matrix by matrix Z, is simply the Frobenius norm of the difference between these 2 matrices. And the goal of PCA is to find a rank D approximation matrix M hat such that it minimizes the reconstruction error. Okay, so we talked about 2, and let me say one more point. It's easy to observe that this matrix M hat, which is the solution to the PCA problem, you can write it as the original matrix times a rank D orthogonal projection. So it always takes this form. And I will come back to this note later in one of the proofs. Okay, we talked about 2 different formulations of PCA, why these 2 formulations are equivalent. I explained it by a simple example. Let's consider these blue points on the plane. And the orange points are their projection into the dashed line. So the pink arrow is showing the variance of the projected points. And the dashed yellow lines is showing the reconstruction error of the blue point with respect to the orange point. Now, let's zoom into one of the blue points on the right side. So as you can see, the variance that each yellow point is contributing to the variance of the projection, a square root of this plus the square root of the reconstruction error is always a constant value. It's just the distance of the original point to the origin. So therefore, the sum of variance plus the sum of reconstruction error is always a constant value. Therefore, minimizing one is equivalent to maximizing the other. And the reason that I talk about both of these formulations is that when I talk about algorithm, sometimes I switch between one notion to another. So it's good to establish it here that maximizing the variance is equivalent to minimizing the reconstruction error. Okay, why is it important to study fairness for PCA? So PCA is not only used in computer science and machine learning, but also in social sciences and natural sciences as a pre-processing step. As I said, for example, in biology, they do PCA. An expert comes, looks at the 2 or 3 dimensional visualization, and then they do some pattern analysis on the data. What I will show here is that PCA can, if you have different demographics in your data, PCA can represent these 2 different demographics with different fidelity. And therefore, it could inject some bias into whatever machine learning pipeline that you have that's coming after. And I would claim that this is actually a kind of bias that is even harder to detect at the end of your pipeline because it happened at the beginning and then you did a lot of processing after that. So it's important to mitigate this bias right at the beginning. So we ran PCA on multiple data sets. This is the result on labeled faces in the wild data set, which is an image data set for celebrity faces. And we saw that we did PCA, and we looked at the average reconstruction error for male population and average reconstruction error for female population. And what we observed when we projected the data into the first 20 dimensions given by PCA was that PCA is constantly doing a better job for male population compared to female population. So it might not be clear how badly this difference is. So let me zoom in. So in 20 dimensions, if you look at the difference, PCA is giving on average 10% more error for female population compared to male population. So this is a male-dominated data set. So we thought that that might be the problem because PCA is a mathematical formulation, like it looks at all of the data. So if your majority is one population, it's natural to focus on that. So what we did next is that we sampled 500 females and 500 males from this data set. But again, we observed a similar pattern, that PCA is constantly doing a better job for male population compared to female population. Okay, this was our motivation to study Fair PCA. So how can we define Fair PCA? So originally, PCA treated your data set as a whole, but now we care about these two populations in the data. So how should we define our optimization problem with respect to these populations? Suppose that the upper part of your original matrix is population A, the lower part is population B. So originally, you were looking for a matrix, rank the approximation matrix U, right? That is good for the whole population. But now, one natural variation that comes to mind is that look for a rank the approximation matrix U that when you look at the average reconstruction error of population A and average reconstruction error of population B, you minimize this maximum. So you kind of want to balance the average reconstruction error for these two populations. This is a natural variation that came to our mind at the beginning, but there's a problem with this. So let's consider this example. Let's say that group A are the blue points on the circle, and group B are the red points on the line. Then what happens is that suppose that you want to go from 2D to 1D. So you want to find a line to project your data into this line. When you look at the blue points, since they are on a circle, whichever line you choose, there will be high reconstruction error for them. Okay, so there's no good solution. But for red points, you have a clear choice. If you choose the horizontal line, you can zero the reconstruction error for them. But this min-max does not necessarily guarantee that you will output the horizontal line. You might end up outputting the vertical line, which is bad for both populations. In other words, the solution to this min-max is not Pareto optimal. So we found this not appealing. So to fix this, what we did was that to fix this, what we did was that we defined a notion of loss. What is loss? So we said that let's isolate each population, okay? And what if we do PCA only for that population? What is the reconstruction error, right? This is the best that you can do for that population, right? Now you have another population in your data, and as the result of presence of this other population, now you're outputting something else, which is giving higher error for each of these populations, right? Let's consider this difference as the loss. How much extra error do I have to pay as a result of having the other population present in the data set? So we call this loss, and we changed our optimization. Right, let me also say this here. A very obvious observation is that when you consider loss of a population with respect to its optimal rank the approximation, right? The best that you can do for that population, loss is 0. They are not paying anything extra. You're giving them the best that you can. Similarly, loss of B with respect to B hat is 0. I will come back to this later. Okay, so with this definition of loss, we define Fair PCA problem as find a rank the approximation matrix U such that it minimizes the maximum average loss for two groups. Okay. Is everything clear here so far for definition of Fair PCA? Yeah.
It's totally clear, but I guess one thing that confuses me is like, is it, say in that example, you find a line which aligns that passes. Isn't that like unfair? Now you've done a good job. Now you've like definitely done a good job on one, and not done a good job on one.
So the thing is that for the other group, you cannot do any better. Even if you choose the vertical line.
Right, but still, like how the error between groups would not be affected by it. Maybe it's just the cost of fairness that you had to do worse on. In order to be fair, you have to do worse on. I guess I don't see why is loss the right way to measure fairness. Why is like equalizing loss the right way to measure fairness?
So I think there are definitely researchers that want to equalize the cost, which is what you're saying. I think it's more like an ad hoc choice that we made, that we felt like we should not hurt one population without benefiting the other one. Okay, if I can benefit both, great. If I'm benefiting one with like disadvantaging the other, that's not good either. But if I can benefit one without disadvantaging the other, why not? Yeah.
So, because this problem is not using the label of, say, male or female, and it's completely unsupervised, I have trouble understanding the source of bias. So, like in the example where you separated the data into two populations and you plotted the errors. So, did you take the line where you randomly sample, say, 100 males and 100, like equal number of males and females? And
Right.
where did that line lie with respect to the lines where the population is separated?
I don't clearly understand. So we have the labels everywhere, even here. That's how I can look what is population A. What
You're not using that to do classification.
to do Fair PCA, I'm using it, but to do PCA, I'm not. So let me go back. So you're talking about the second plot, right? Can you repeat your question?
So, if you separate the two populations and you separate and you perform PCA on them, you get differences in the error. But if the population is mixed,
Right.
does the error is it somewhere in between, or does it align closely with one of the populations?
So note that when I run PCA, the populations are not separated. They are mixed. So I put males and females mixed together. I do PCA for the whole data. Now PCA is blind to male and female, right? And then it outputs some projection for the whole data set. It outputs some low dimensional representation, right? Now with respect to that low dimensional representation, I can only look at females, right? And see how good is this representation for females? How good is this representation for male? And that is what I'm measuring here. So it's not PCA only for each of them. It's PCA for the whole. But then seeing how good is this PCA for the whole for each of them. Is it clear? Okay, we can talk more offline. Yeah.
I'm wondering how do you consider the reconstruction error equals clustering test? Say if you want to do the PCA first and you do the classification, then how this difference equals that classification error?
Yeah, that's a very good question. We didn't study that, but like to run experiments to see, or even theoretically see how would it amplify after you do classification. Yeah, but that's a very interesting question. Yeah. Do you mean that do we normalize the variance before we run our experiments or not? Or so yeah. With the image data, I believe that for each feature, we did the variance 1. So we made the variance 1 over all the features, which is a standard thing to do PCA in applications, to first make the mean of your whole data 0 and then the variance 1 over each feature, so that if you have, like, for example, if one feature, so for image data set, probably it's not very crucial, but for example, we ran it on another data set which was on credit data, and one feature was like household number, which was 1, 2, 3, 4, 5, for example. Another feature was income, which was in terms of 100,000. So for that, normalization mattered more. Yeah.
Would you consider trying something like bootstrap resampling to see if that would kind of solve the issue? Because if you do one set of samples from the higher distribution data,
Mm-hmm.
then you're potentially not getting a real estimate of what the variance is. But if you did bootstrap resampling, you did a lot of different bootstraps.
Uh-huh.
You might get a different average distribution that might be more closely to the line. Would you consider that as a comparison?
We did not. That's interesting. We didn't look into that. There was one question. Yeah. So that's a very good question, and I think that's a mystery for myself. But and there is some follow-up work that are just looking into that. That what is it about images specifically that is making this happen? My guess, from talking also to other people who work on vision, is that there are much more variance on female faces. That if you want to choose one subspace for both populations, that subspace can better represent males because there is less variance in their faces than females, but females, you lose more information. That's a guess. Yeah. Okay. Oh, thanks. Okay. Okay, so we are hopefully clear on the definition of Fair PCA. We want to find a rank the approximation matrix U, which minimizes the maximum average loss over two populations, right? Our first observation is that the solution to the Fair PCA problem, it has the same average loss for two populations. So this is great. We were looking for a min-max solution, but we ended up in something even stronger, that it gives the same average loss. I would like to briefly go over the proof. Remember that for the original PCA, I said that the solution could be written as the original matrix times an orthogonal rank the projection matrix, right? There's a similar observation for the min-max variation, that the solution could be written as the original matrix times VV transpose, where VV transpose is an orthogonal rank the approximation. Now rewriting loss with this presentation of U, one can see that loss of A with respect to the solution that is result of the Fair PCA is simply the Frobenius norm of the optimal rank the approximation for A hat, minus the Frobenius norm of A. So let's say variance in the optimal rank the approximation minus the variance of the original matrix plus the Frobenius norm of A minus AVV transpose. So note that this last term is nothing but the reconstruction error of A with respect to the projection, right? Similar observation holds for loss of B. So simply, we can write loss in terms of a constant value minus the reconstruction error. Okay, and we can show that if we look at this function, reconstruction error of A with respect to its projection using VV transpose, that the value of this function at all its local minima is simply the reconstruction error of A with respect to its optimal approximation. Therefore, now if we look at any local minimum, V star transpose, and now if I write loss with respect to V star transpose, the loss is equal to 0. Okay? Okay, so from this slide, just remember that this function at all local minimums, the loss is equal to 0. Okay? Okay, so what was our optimization? We want to minimize the maximum average loss, right? So for contradiction, assume that the average loss for group A is bigger than the average loss for group B. Okay? Then from this maximum, the average loss for group A will come out, right? U is a global minimum for our optimization. Therefore, UA is a local minimum of loss A. Now remember what we talked about in the last slide. Because it's a local minimum, loss is 0 at U, which is equivalent to AVV transpose. But we assume that loss of A is strictly bigger than loss of B, which is a contradiction by this loss being 0. Okay? So we proved that the average loss at the optimal solution is the same for two populations. Okay, but how can we find the solution to the Fair PCA problem? In the next step, I will propose an efficient algorithm that finds an approximation matrix V star that we guarantee that the rank of D star is at most D plus 1. Remember, we want to rank D approximation matrix. And it achieves the optimal Fair PCA objective value for D dimensions. Okay. Okay, how does our algorithm work? So we can write loss in terms of the variance of the optimal rank D approximation minus the variance of your data now using this projection matrix, right? Remember the switch between variance and reconstruction error for PCA. We have similar intuition happening here. Now, using this formulation, we can write an STP relaxation for our min-max. We want to minimize Z such that Z is bigger than average loss of group A, average loss of group B. So originally, we want the rank to be smaller than D, right? We relax it to trace of P is smaller than D. And P here is the projection matrix, right? Originally, it was VV transpose with some special structure, but now we generalize it to any projection matrix. Okay, this is an STP, we can solve it. So let P and Z be a solution. The problem is now P might be high rank, right? It's an n by n matrix, and we only have a constraint on trace of it. So we might have a lot of fractional eigenvalues, okay? So how can we do now reduce the rank of P? Here we do a trick. So let P and Z be the solution to the STP. We take this solution. Now we write the singular value decomposition of P. Let it be lambda hat J, UJ transpose. Now we rewrite the STP. We fix UJ transpose, but this time let the lambda J hat vary. And why are we doing this? Remember that like the solution of STP, it might have a lot of fractional eigenvalues, right? Now, using like the properties of LP, I want to shift these eigenvalues around to make them integral. Okay? So now this is an LP in terms of lambda J. I know that an extreme point solution, it should have n plus 1 tight constraints. So either n of them are coming from eigenvalues being 0 and 1, and 1 is coming from sum of eigenvalues equal to D, then it's perfect. We have exactly D ones and the rest of them 0, so we have a rank D approximation matrix. The other case that could happen is that the first 3 constraints are tight and we have n minus 2 from the last one. Okay? In this case, D of lambda J stars are 1, and you have 2 fractional eigenvalues, which results in P star having rank at most D plus 1. But note that here, because the first 3 constraints are tight, the loss, so z bar is equal to the average loss and for group A, and z bar is equal to the average loss for group B, so the average loss is still the same. Okay, so we either find a solution of rank D, perfect, we are happy, or the solution is rank D plus 1, but still we are guaranteeing that we are giving them the same loss, and our objective value is, in terms of reconstruction error, is smaller than the objective value for D. Okay, what is the running time of our algorithm? The heavy computational part is solving the STP. It's order of n to the 6.5. I don't recommend it in applications. What we did in applications for running our data sets in real life is that we use multiplicative weight update. It's a heuristic approach, but under certain conditions on the functions, we can give guarantees of its convergence. And in practice, we get high accuracy very fast. And this is the method that we use for running our own algorithm. Okay, so let's go back to the data sets and see now how is Fair PCA performing compared to the original PCA. So these two plots are showing reconstruction error for each population when you run PCA and Fair PCA. This is what we naturally expect to happen. For both Fair PCA and PCA, when the number of features or dimensions is increasing, we expect the reconstruction error to decrease, right? But these two plots does not clearly show what's happening now in terms of fairness and loss. So let's zoom in and look at what happens in terms of loss. So the green line in both of the plots, one of them is for labeled faces in the wild, the other one is for credit data, which is another data set that we used. So remember that using the Fair PCA algorithm, the average loss will be the same, right? That's why we have only one green line for two populations. The orange line and the blue line shows the average loss of male population and female population when you use regular PCA. And as you can see, there is a huge gap between two losses. But Fair PCA is outputting the green line, which is kind of doing something in the middle. We have a similar observation for the credit data. Okay, great. So the setting that I discussed was for the case that we have to, yeah?
That's on the last slide. So why should loss be the right idea here, right? So it seems to me that the reconstruction error is much more practical than the loss, average loss.
So average loss is a measure that we consider for how fair the algorithm is, but in practice, but at the end of the day, you can use the Fair PCA algorithm, and if you like to measure the reconstruction error, you can use the reconstruction error. Is your question why is loss the correct thing?
You know, at the end of the day, you know, somebody might say, oh, I've got 10% error in this subpopulation, right?
Mm-hmm.
Like that seems to be the takeaway or the main point. That was the motivation, right? For finding a fair algorithm. But
Right.
Plot one in the corner might suggest that there's still some bias.
Right. So in terms of reconstruction error, so in terms of reconstruction error, we had improvements. I think the reason that I showed loss was that it was more clear, the gaps. But I should have zoomed in on the reconstruction error, then you would have seen the difference. So the blue line is for female when you do regular PCA, okay? When you do Fair PCA for female, you have the red line, which is shifted at the bottom. I just saw that.
So there's overlap in that bottom line, right? So the green dash and I guess the red.
So okay. So the green dash, if you can see here, is a bit higher than the purple dash, right? So you are increasing the reconstruction error for males in the Fair version, but the red one is lower than the blue line for females, so you're decreasing it for female. But that's a good point. Maybe next time I zoom in there. Yeah. For Fair PCA, you mean, or? I think because by nature, the way we are designing our optimization problem, like you want to balance these two losses, right? So the optimization problem is pushing this constraint that I don't only care about minimizing z, but at the same time, I don't want the difference between these two to be very high. Oh, you mean for credit data and this other one? So, I mean, I see huge gaps in both of the data sets. What do you see in, what do you mean by difference exactly? Uh-huh. Oh, I see what you're saying. So for the right data set, the original data set was in 22 dimensions. Okay, so when I project to 22 dimensions, everything is 0. I mean, original dimension, right? That's the problem. But for label faces in the wild, the images were, I think, 48 by 48 pixels, so 1,700 dimensions originally. So even when you go to 20, still you have huge error numbers. Sure. Okay, so we discussed our setting for the case that we had 2 demographics in our data. Our algorithm and our setting could naturally be extended to the case that you have m demographics. Then you need m-1 extra dimensions. In a follow-up work, we improved this, and that is, we call that multi-criteria dimensionality reduction. I will say in a second why, because we generalized the whole setting. But for 2 groups, specifically, the algorithm that I explained, it needed 1 extra dimension, right? But we proved that going to the extreme points of the same SDP that I showed you will actually give you the exact d-dimensional solution. So for this, we proved some properties of these extreme point solutions of the SDP and their structures. For M groups, the same analysis on these extreme points of the STPs show that we can improve from m extra dimensions to a square root of m. And of course, you want to ask how hard is the problem in general. For general M, the problem is NP hard. Okay? So I want to spend maybe only 1 slide now talking about that this framework that I discussed was for principal component analysis, but we generalized it to a wider class of dimensionality reduction techniques. So for principal component analysis, if you look here, so this is the projection matrix that you're looking for. And for each demographic, you were considering reconstruction error or loss, right? Loss is a linear function of reconstruction error, so F1 would be that. And G was, sorry, let's switch to variance. So F1 was variance in terms of the projection, and G was simply minimum. You want to maximize the minimum variance, right? So we generalized it. Now G did not have to be minimum. It could be any concave monotone non-decreasing function. And Fi does not need to be variance or reconstruction error. It could be any function linear in your projection matrix. Okay? And 2 famous examples of this for M equal to 2 group would be Fair PCA and Nash social welfare objective. So you might say that, oh, min-max over variance or reconstruction error, it's not something that I'm looking for. I'm looking for optimizing the Nash social welfare. Then you can still use the setting. Okay. So in the second part of the talk, this part will be more brief. I want to talk about another problem in the context of representational bias, which we call it fair spectral clustering. Okay, I'm sure, again, many of you are familiar with the spectral clustering, but a quick recap. Spectral clustering is a standard method of choice for clustering your data when your data is well represented as a graph, right? It could be a social network where people are nodes, and you have the weights on edge between those 2 people are showing their similarity or their friendship. It's also used in image segmentation and speech recognition. So the variant of spectral clustering that we are interested at, I can well explain it by an example. Suppose that you're in a high school, and you know the academic performance of the students. Okay, so let's represent these students as nodes of the graph, and the weighted edges between 2 students is how their academic performance is similar to each other, right? So now you want to put these students into different classes. You want the students with similar knowledge to be in the same class, right? So that would be the standard clustering, a spectral clustering algorithm. But now you have this extra condition that you want each classroom to be diverse. Or in other words, you want them, for example, if you look into gender and you have like 3 females and 3 males, you don't want to end up with a cluster that has like all females in one cluster and all males in another cluster. You rather are looking for the right one, which has half of the population of each cluster males, half of them females, okay? So I would like to think about it more as having balanced clusters in terms of your demographic, but I call it fair mainly to be consistent with the literature, because this was a fairness notion introduced by Chiericetti et al. In 2017 that says that whatever distribution of demographic that you have in your original data, now you want to kind of have it in each of your clusters. Okay. Yeah, Chiericetti et al. Studied this for 2 groups, for K-center and K-median clustering. Then Rosner and Schmidt, they generalized it to multiple groups in the case of K-center. And Schmidt et al., they considered it for 2 groups for K-means. Okay, so our goal is to study a spectral clustering with this balances or fairness constraint, right? And going back to the example of this simple network that we have, if we run a spectral clustering on this network, this is the output. And as you can see, the clusterings are highly unbalanced. The top one is only female, the bottom one is only male. Okay, so let's first review the setting of spectral clustering. Then I will tell you how we can incorporate this balances or fairness notion into this setting. We have an undirected graph G with n nodes, and there's a weight on the edge between I and j, which shows a similarity between I and j. Okay, and in this talk I will focus on unnormalized spectral clustering, but similar setting holds for the normalized case as well. So unnormalized spectral clustering wants to minimize the ratio cut value of your cluster. So the cut value of a cluster is simply look at that cluster and all other nodes in the graph and see what is the sum of the weights that cross between this cluster and all the nodes. And the ratio cut says that, okay, now take the sum over all of these values. So the original spectral clustering wants to find a clustering which minimizes the ratio cut value. This is NP hard. So what happens is that we relax this minimization problem. So to explain the relaxation, I need to explain in how we encode a clustering. So matrix H is simply just a matrix that represents your clustering. So it's n by k. So for each node of the graph, you have 1 row. And for that node, you look which cluster does it belong to. And you put 1 over a square root of the size of cluster there. Okay? You don't need to go into the details. Just remember that the matrix H is representing the clustering. And with having H, you can recover clustering. With having the clustering, you can recover H. Okay, so now using H, you can rewrite the ratio cut value as trace of H transpose LH, where L is the graph Laplacian matrix. So then the spectral clustering is this minimization. You want to minimize the ratio cut value, trace of H transpose LH, subject to H representing a clustering, right? We relax this to minimize trace of H transpose LH. Now we relax the condition on H having this a specific form of representing a clustering to H transpose H equal to the identity. Okay. Now note that at this step itself, then H is not representing a clustering anymore. You might end up with the H that has like not only 0 and 1 over a square root of the size of the cluster on its coordinates, but it can have values everywhere. So you solve this, you find a matrix H, but as I just said, this H does not represent a clustering. So you run k-means on rows of H. Note that H is now an n by k matrix. So it's like you switch your dimensions. Now you have n vectors in k dimensions. You do k-means on these n vectors. Okay, and this is the output clustering of the spectral clustering. Okay, this is what conventionally is done in unnormalized spectral clustering, and as it is obvious, the solution to this relaxation, there is no guarantee on how close it is in the cost to the exact form. Okay? So now we have this fairness constraint that we want to have clusters that are balanced, right? So this is slide. I mainly only want to say how we write this fairness constraint of each cluster being balanced as a linear constraint on my clustering matrix edge. Okay? So you don't have to even go into the details. You just need to know that f of s, let it be the identifier for each demographic, which means that, let's say male and female. For females, I have an n-dimensional vector. Just for each node, I'm saying that which places I have female there, right? Okay, and this lemma essentially is saying that the condition that we had that, let's say this is female and this is cluster L, the fraction of females in cluster L, I want it to be equal to the fraction of females in the whole population, right? This lemma is just saying that this could be translated into this linear constraint on matrix edge. Okay? Okay, now I write all these identifiers of demographics in a matrix F, and now I can simplify all that condition on clusters being balanced as F transpose H equal to 0. Okay, so now this is the spectral clustering with fairness constraints. And you can simply see that with a change of variable, okay, you can rewrite this as the original spectral clustering. That is not, that's an easy step. And then you can just solve it like you solve a spectral clustering. So I think I didn't say this point, but the way you solve the original spectral clustering is that you simply output matrix H, which has the k eigenvectors corresponding to the k smallest eigenvalues of the Laplacian matrix. Okay? Doesn't matter. What matters is that this is a constrained version. We can transform it to the original version. We can solve it efficiently. This was not something new. Constrained spectral clustering has been done before, especially for the case that you have some muscling constraints, like there's a bunch of nodes that you say that these two have to be in the same cluster. And since we are adding our fairness constraint to the relaxation, right? Remember that H does not represent a clustering itself. We do not guarantee a fair clustering. It's just that we're adding this constraint and it's guiding the spectral clustering that if in your underlying data you have multiple clusters and one of them is more fair, pick that one. Okay, so to test the validity of our method, we consider the variant of a stochastic block model. A stochastic block model is a famous graph representation model that has been used to test validity of a spectral clustering. But now that we have both demographics and clusters in the data, we have to define a variant of this. So we put an edge between two nodes in this graph with probability A if they are in the same group and in the same cluster. We put an edge with probability B if they are in the same group but in different clusters, and so on and so forth for probability C and D. The only important thing here is that A is larger than B, larger than C, larger than D, which specifically means that being in the same group is stronger than being in the same cluster. Okay, so here's an example of such a graph generated for two groups using this stochastic block model. So the red points show, say, demographic A. Blue points are showing demographic B. And if you run a regular spectral clustering on this graph, what happens is that it will output V1 and V2. Okay? One of them is completely demographic A, one of them is completely demographic D, so they are highly unbalanced. But if you run our fair version of a spectral clustering, it will output C1 and C2, which are completely balanced. Okay. Okay, so now we theoretically guarantee that on this variant of a spectral clustering, we can recover the underlying fair clustering of the data, which is this clustering that we had here, C1 and C2. So essentially, we are saying that, for our theoretical guarantees, we consider a special case that all of your clusters have the same size, and all of your demographics also have the same size. And also, in each underlying fair cluster, each of the demographics are the same size. So this is a super uniform, everything nice case that we consider. And for this case, we can prove that if the probabilities that I considered here, their difference is high enough, then with high probability, I can recover almost all of the points in the underlying clustering. Okay? So this was for the theoretical guarantee, and we proved this by looking at eigenvectors and eigenvalues of the expected Laplacian matrix, and proving that with high probability, these eigenvalues and eigenvectors of the observed Laplacian matrix are close to the expected Laplacian matrix. This was for the theoretical guarantee. In applications, we don't have such strict conditions on our data. So here are our experiments on a stochastic block model. So I have lines for normalized spectral clustering too. You can ignore them. Just here, look at the circles and look at the red line. Okay. So error is how much fraction of the points I'm labeling correctly. Okay. You have an underlying fair clustering, right? You know the label of each point in that clustering. Now you want to see that using regular spectral clustering and fair spectral clustering, how much fraction of those labels you can recover correctly. So the red line is fair spectral clustering. As you can see, as the number of points grows, like the error converges to 0, but the regular spectral clustering is the line at top. Okay, the performance doesn't change. So the next plot is showing the case that our probabilities are much smaller. So we have a much more sparse graph, which is harder to cluster in general. Still, our unnormalized version, the error is converging down. And if you're wondering, the blue line is a normalized spectral clustering, is doing great, but it's very slow in applications. And finally, the last plot, as I said, for our experiments, we showed that this actually works even if your data and underlying clustering does not have all those conditions. So for this plot, our clusters have different sites. Okay? And we still show that our algorithm can recover the labels. Okay, and my final slide is by showing our experiments on real data. So we considered a bunch of data sets: friendship network, Facebook network, and drug network. And what happens is that, so the blue line is showing how balanced are your clusters on average, okay? And the red line is showing the ratio cut value, because these are two kind of competing factors, right? For the ratio cut value, you care that you have a strong connectivity in each cluster. But for the balance, you care that they are balanced in terms of different demographics. So as you can see, the dashed line is our fair version, and the solid line is the normal spectral clustering. So with the dashed line, as you can see, we are increasing the balance in all of the data sets. So, and this is coming with minimum change to the ratio cut value. Yeah?
So average balance, something like how well the proportion represents the population proportion?
Yeah, so average balance means that suppose that in one cluster you have 30% male, 70% female. Then the balance would be 7/3.
So it's the worst cluster balance?
Yes.
Okay.
Yeah. Yeah, so in the last plot, we are increasing the balance a lot, but it's coming as an increase in the cost of the ratio cut value. So we're losing a bit in the connectivity inside the clusters. Thank you so much. This was all I had to say today. If you have any questions.